Okay, can I have everyone's attention, please? So let's go ahead and start. And before I begin, I wanted to know, are there any questions? All right, so if you guys remember, we talked about the relationship between the cell potential and the equilibrium constant last time, and we derived an expression. And this comes from, we know that the relationship between free energy and the equilibrium constant is delta G naught reaction equals minus RT ln K. We learned this last quarter when we looked at thermodynamics and we looked at the relationship between free energy and the equilibrium constant. Now we also know that delta G naught reaction equals minus NF E naught cell. That's the relationship between the cell potential and the free energy. And therefore we can say NF E naught cell equals negative RT ln K. And so now we can rearrange to get rid of the two negative signs. We can either get rid of this and say ln K equals NF over RT E naught cell, or we can say E naught cell equals RT over NF ln K. So depending on what we want to calculate, you can rearrange this equation to get either this or this. And then we said that if you take R is a constant, it's 8.3145 joules per Kelvin per mole. We said that temperature is absolute temperature, and if we're at room temperature, which is temperature here is Kelvin temperature, and if we're at 25 degrees Celsius, then this would come out to be 298.15 Kelvin. And then lastly, we said that F is Faraday's constant, which is 9.6485 coulombs per mole. And so if we put this in, and we end up with RT over F equals 0.025693, 0.025693 volts. And so you can put that value in there, and so what you'd end up with is ln K equals N over 0.025693 volts, or we can say, we can write that like that, or we can say E naught cell equals 0.025693 volts divided by N times ln K. All right, so now we have a relationship between the equilibrium constant and the cell potential. So let's take an example where we apply this. Okay, so if you turn to that problem on the worksheet, and so if I may change this to the problem, you can see that you're asked to calculate K, which is the equilibrium constant, for the reaction that we've been looking at all along, which is the reaction in the Daniell cell. And we know that the cell potential for the Daniell cell is 1.10 volts. And so if I want to calculate the equilibrium constant, can everybody see that this would be making use of this equation over here, where we're going to say ln K equals N E naught cell over 0.025693 volts. So we're going to say ln K equals N, which is the number of electrons being transferred, E naught cell divided by 0.025693 volts. Now we know, we've seen previously that for the Daniell cell, we know 2 electrons are being transferred, and N gives you the number of moles of electrons being transferred. So that would be 2. The cell potential, we know for that is 1.10 volts. Now, if they don't give you the cell potential, you look at the balanced equation, you figure out what is the reaction of the anode, what is the reaction of the cathode. Then you would go to the electrochemical series or the table of reduction potentials, and you add them together. You take the reaction for the cathode, you take the reaction for the anode and switch the sign, and then you add them together, and that will give you the cell potential. So once you get the cell potential from the tables, you figure out how many electrons are being transferred, and then you put this in here, and this will be 0.025693 volts. Volts and volts will cancel out, which gives you 85.7. All right, and then if I take the inverse log of that, K comes out to be 1.5 times 10 to the 37. So you can see for this reaction, the equilibrium lies entirely on the product side. So when equilibrium is established, you're going to get lots and lots of products being formed. All right? Now, if you look at this reaction, can everybody see that when we're looking at K, K represents the concentration of the products divided by the concentration of the reactants. All right? Now, there are solids here, and we know that if you have solids, then you do not include them in the equilibrium expression. So K is really the concentration of zinc 2 plus ions, which are the products, divided by the concentration of copper 2 ions. All right? And so this is one way in which you can determine the equilibrium constant for a reaction, because essentially what you do is you can look up the appropriate oxidation reduction reaction, and from that you can get the, from the standard reduction potentials, you can figure out which is the oxidation half of the reaction, you can figure out what is the reduction half of the reaction, figure out the potentials that correspond to the oxidation half and the reduction half, add them together, that'll give you the cell potential. Once you get the cell potential, if you put it in this equation, you can figure out the value of the equilibrium constant. All right? Yes, go ahead.
Why is K in 2 significant figures?
Why is K?
In 2 significant figures. Why is it in 2?
Oh, why is it 2 significant figures? Because actually, we are going to 3 significant figures here, all right? And so if you were strictly keeping track of sig figs, then you would just take the decimal because you're taking the inverse log of that. Okay? So strictly speaking, you would end up with a number that is 1 sig fig. All right? But I'm just carrying it over. So here I'm not keeping track of sig figs. All right? So if you, does that make sense to everybody? If this is, we're taking the inverse log of this number, and when you go from the log scale to the regular scale, you want to look at the decimals. All right? And so it would turn out that this number should be, if you're keeping track of sig figs, should end up with 1 significant figure. Got it? Okay, so we talked about the fact that for any reaction, you can figure out what the equilibrium constant is as long as you can identify the oxidation half and the reduction half of the reaction. Okay? Now, I want to kind of summarize sort of the relationships that we've looked at. And, when you are looking at thermodynamics, all right, and you want to relate delta G, which tells, if you're looking at spontaneous reactions, delta G should be negative. If it's a non-spontaneous reaction, delta G would be positive. And the relationship between delta G and equilibrium constant is given by this equation where we know delta G equals minus RTL and K. And if you want to look at the relationship between delta G and cell potential, we know that relationship is given by delta G equals minus NF E naught cell. And then if you want to look at the relationship between the cell potential and K, that's the equation that we derived, all right, today. And so if ever you have to convert from one to the other, this kind of triangle shows you the relationship between the quantities, the relationship between delta G, the cell potential, and the equilibrium constant. So when you're solving problems, depending on what you need to calculate, you can use that to figure out the relationships. Is that clear to everybody? So now, having said that, we're going to look at sort of the last topic that we're going to look at in terms of galvanic cells, and that is the Nernst equation. Okay, so if you're copying this, I'll give you a moment to copy it down. All right, so yes, go ahead.
Where are you getting that decimal number, the 0.0256? Where did that come from?
That comes from, remember, it's RT over F. So R is the gas constant, which is in SI units, which is joules per Kelvin per mole, at times T, which is the temperature, which is 298.15, and then F is Faraday's constant. Okay? So if you put those numbers in, you should end up with that. Okay, so if we now move on to looking at the last topic that we want to look at when we deal with galvanic cells, and that is what we call the Nernst equation. Now, when we started looking at galvanic cells, one of the things that we talked about was that for any battery or any galvanic cell, we know that as the battery is being used up, at some point the battery gets spent. All right? And so usually what happens is when we deal with galvanic cells, we start under standard conditions. So if you're dealing with a Daniell cell, we're going to have 1 molar concentration of zinc ions, 1 molar concentration of copper ions, and then we have zinc metal and copper metal. And at that point, when we connect the circuit, because the concentrations are all under standard conditions, the voltage that we would measure on that voltmeter would be 1.10 volts. Okay? Now, once the battery starts working, what's going to happen is the concentrations are going to change. The concentrations in the anode, where we have the zinc ions, their concentrations are going to change. And on the other side, the copper ion concentrations will change. And so as the concentration changes, the cell potential starts changing as well. All right? And as the reaction proceeds, the cell potential changes as well. Until in the end, the battery is spent. And when the battery is spent, we said that an equilibrium has been established. And when an equilibrium is established, we know delta G is 0. All right? And so the cell potential is 0 as well. So what happens is when a battery is spent, essentially what happens is that an equilibrium has been established, and the reason is that as the reaction progresses, the concentrations in both those chambers, in the anode and the cathode, will be changing. Okay? So if we want to look at the dependence of the cell potential on concentration, then we look at the Nernst equation. All right? So what the Nernst equation gives you is the formula for predicting the variation of the cell potential with concentration or concentrations and pressures is expressed by the Nernst equation. All right? And once again, we're going to start with the equation that we learned in thermodynamics. Now, if you want to look at the change in free energy as the concentrations of reactants and products change, we said that is given by the equation delta G reaction equals delta G naught reaction plus RT ln Q. And remember, we said as the reaction approaches equilibrium, if you want to look at how free energy changes as the concentrations of your reactants and products change, we're using Q because we haven't established equilibrium yet. The reaction is proceeding, and if you want to look at the dependence of the free energy on changing concentrations of reactants, this is the equation that we use. All right? Now we're going to apply this to electrochemistry. In electrochemistry, we know that delta G reaction will give you minus NFE cell, and delta G naught reaction. So this is free energy under conditions where you're not under standard conditions. This is free energy under standard conditions, which gives you the difference in free energy between pure reactants and pure products. All right? And in this case, this will be under standard states for the cell where everything is 1 molar concentration. So this will be NFE naught cell. And now I'm going to take these two values and put it in that equation. So what I'll have is NFE cell equals minus NFE naught cell plus RT ln Q. And if I rearrange this equation, you can see E cell equals E naught cell. And I'm going to take these signs and flip the signs around. So it'll be minus RT over NF ln Q. And we call this the Nerst equation. And essentially what this equation tells us is that as the concentrations of your cell, your reactants and products in your cell changes, if you want to look at the dependence of the cell potential, how does the cell potential change as your concentrations of your reactants and products vary, that's given by this equation. Now if you guys remember, RT over F is 0.025693 volts. So if I replace that in this equation, I can say E cell equals E naught cell minus 0.025693 volts over N times ln Q. So if you replace all the constants and put the values that correspond to those constants, they come out to that number, and I can replace those numbers, that is RT over F, with that. Okay? So now let's apply this in a problem. Okay? And so let's take this example where we're asked to calculate. So calculate the potential at 25 degrees Celsius of a Daniell cell in which the concentration of zinc ions is 0.10 moles per liter, and that of the copper ions is 0.0010 moles per liter. Okay? So if we were calculating the standard cell potential, we know that's going to be 1.10 volts. All right? And that we can get from the tables of standard reduction potentials. Okay? We can calculate by the standard cell potential would be the reduction potential at the cathode plus the reduction, flip that around, and the potential at the anode, and you sum them up. If it's going to be under other conditions, then we're going to use the Nerst equation. So we know that if you have, let's look at what's given to us. We know that the concentration of zinc ions is 0.10 molar. The concentration of copper ions is 0.0010 molar. And we know that the standard cell potential for the Daniell cell is 1.10 volts. Now, what we need to calculate is the cell potential when it's not under standard conditions. All right? And so we know that E cell equals E naught cell minus 0.025693 volts divided by N times ln Q. All right? Which is E naught cell minus 0.025693 volts divided by N. And we know ln Q is the concentrations of the reactants and products. And we know for the Daniell cell, the reaction that we're looking at is zinc solid plus copper 2 plus aqueous, giving me zinc 2 plus aqueous plus copper solid. So the equilibrium expression, or the expression for Q, would be the concentration of zinc ions divided by the concentration of copper ions. All right, that's what Q would be. And therefore, I can say E cell equals 1.10 volts, which is E naught cell, minus 0.025693 volts, divided by N. Remember, N gives you the number of moles of electrons that are being transferred. So how many moles of electrons are transferred in that balanced equation? 2. All right, so we're going to put 2 there. And then this will be ln times the concentration of zinc is 0.10 molar divided by 0.0010 molar. All right, and so what I'll end up with, E cell equals 1.10 volts minus, and if you put all these numbers into the equation and solve for it, it comes out to be 0.059 volts. And if you subtract that, it comes out to be plus 1.04 volts. All right, so you can see the cell, when you have 1 molar concentration of zinc and 1 molar concentration of copper, and that's the cell potential under standard conditions, it'll be 1.10 volts. But as the reaction proceeds, now you can see the cell potential decreases as the concentrations change in both chambers. All right, and this will be the cell potential when the concentrations are the ones provided there. Okay, so if you're given a problem where you're asked to calculate the change in cell potential as the reaction proceeds, and you know the concentrations in the 2 chambers, in the chamber where you have the anode and the chamber where you have the cathode, now you can calculate the cell potential. Got it? So that kind of completes looking at galvanic cells. And remember, galvanic cells take advantage of a spontaneous reaction. Okay? Now we're going to look at cells that make use of a non-spontaneous reaction. And we call this electrolysis, or we call them electrolytic cells. All right? So we're going to look at electrolytic cells or electrolysis. And let's just talk about this a little bit. So in the past, we've looked at the galvanic cell, and we've looked at the Daniell cell in detail. All right? And we've seen this picture of the Daniell cell. Now, Daniell cells take advantage of a spontaneous reaction. There's a natural tendency for the reaction to take place. And because there's a natural tendency for this reaction to take place, we said we construct this device so that instead of both the reactants and products being in contact with each other, we're going to set it up so that we're going to take advantage of the spontaneous reaction, but now we're going to force the electrons through the wire, and as a result, we're going to end up with a current being passed through the wire. Now, in electrolysis or electrolytic cells, what we look at is a reverse process. So now what we do is we're not interested in a spontaneous reaction. What we do is we take this setup, but now we're going to connect it to a power source. So rather than take advantage of a spontaneous reaction, now you're going to connect it to a battery or plug it into a source of electricity. And what we're going to do is we're going to force the reaction to go in the opposite direction. See, so the electron flow, remember before in a spontaneous reaction, the electrons flow this way. Now we're going to force the electrons to go in the opposite direction. And because we're forcing the electrons to go in the opposite direction, now what was the anode becomes the cathode. Do you see that? So now what's happening is over here at this electrode, electrons are getting pulled in. All right? And so the electrons get pulled in. So now what happens is this is no longer an oxidation. Now where the oxidation used to take place, you're going to have a reduction. All right? Now what's going to happen is because we're forcing the electrons in the opposite direction, and we're forcing it by using an external power source, external source of current, and we're going to force it to go in the opposite direction. So now what's going to happen is because we're forcing the electrons to go this way, now the reaction that would take place here would be a reduction. So instead of producing electrons, now the zinc 2+ ions will pick up 2 electrons to give you zinc solid. And this becomes the cathode. And over here now, electrons are flowing out of here. As you complete the circuit, electrons are flowing out of here. So now what happens is copper solid will pick up 2 electrons to give you copper 2+ aqueous. And this becomes the anode. Do you see that? And so what we do is, by using an external source, we're now reversing the whole process. Now this is the underlying principle in rechargeable batteries. All right? So when you purchase a battery, now it's an unused battery, and we'll say that we're starting with everything under standard conditions. So if you start with a galvanic cell, and you start with 1 molar concentrations on both sides, you're under standard conditions. Now this cell will produce a voltage of 1.10 volts. All right? Now as the battery keeps functioning, now the concentrations are going to change. So the cell potential from the standard conditions will start getting lower and lower and lower. And at some point, the battery will get spent. And when the battery is spent, it means that it's established equilibrium, and that's why there's no cell potential. It's 0. Okay? Now what you do is your rechargeable battery, you take it and you put it in a charger and you plug it in. And essentially what you're doing is now you're reversing the process. So now the concentrations, it's going to go in the reverse direction. And remember, initially as the battery gets spent, what's going to happen is that you have zinc ions. The concentration of zinc ions are going to go up as more and more zinc, you're going to have zinc depositing over here, and over here, the other way around. You're going to have copper depositing on this side. So because copper is depositing, you can see the concentration of this goes down. Over here, you have the zinc metal increasing, so the concentration goes up. So in a galvanic cell, the zinc concentration goes up, and the copper concentration goes down. Do you see that? And so your concentrations change until the battery is spent, and now you have different concentrations of both. All right? When you reverse the process, now what happens is they're all going to go back to 1 molar concentration again, because you're reversing the reaction now. And so remember, the zinc ions that were formed and the concentration went up, now will go back to zinc solid. And over here, the copper that was deposited will now form copper ions. And so now you're just running it in the reverse process until you reach standard conditions, and now your battery is ready to go once again. Did you guys get that? Yes?
For the new formulas, wouldn't the electron be on the other side for the anode?
It's being reversed, all right? So what's happening here is that what used to be the anode is the cathode. You mean the electrons being picked up? Yes, I'm sorry. Yes, you're right. Okay? So here, I'm writing so fast, I'm not paying attention. All right? So on this side, it becomes the anode. So what was cathode becomes the anode, and vice versa. Got it? So now, if we're dealing with electrolytic cells, now, so this is the idea behind rechargeable batteries, but if we're dealing with electrolytic cells, we no longer have to keep these 2 chambers separate, because remember, the principle behind galvanic cells was to keep them separate so they don't react with each other directly and try to channel the electrons to the wire. In electrolytic cells, if you're devising an electrolytic cell rather than a rechargeable battery, if you want to just look at electrolytic cells alone, because we are controlling the direction of the electron flow, we do not have to keep the 2 chambers separate. You understand it? Because now we're not taking advantage of a spontaneous reaction. We're taking an external power source to drive the reaction in a certain direction. So we have full control of the direction of the reaction. So if you take an electrolytic cell, then if you want to design an electrolytic cell, not a rechargeable galvanic cell, for example, then what you would do is, this is what an electrolytic cell looks like. All right, they're both in one chamber. Now, by convention, we're going to try to keep the anode on the left-hand side. So this would be the anode. And over here, we'll have the cathode. All right, and we're going to connect it to a power source, all right, where this would be the positive and that would be the negative, all right, and we're going to force the electrons to flow in this direction. All right, and so what we'll end up with is this is where the oxidation will take place. And this is where the reduction will take place. So this is the anode, all right? So can everybody see that I do no longer have to keep them in two separate chambers. I can keep the electrodes in the same chamber because now I have full control of the direction of the reaction, all right? And the external current is going to force the reaction to go in the direction you want it to, all right? And there's no concern about them reacting directly with each other. Yes? Yes, so you're going to find this a little confusing because what I did was I'm taking this, all right, and I'm taking this setup and this is what I'm doing. You see that? All right? And because we always draw everything with the anode on the left side and the cathode on the right side. Do you understand that? So I took this cell, and this is where some people get a little confused because we're reversing the reaction, but actually what I'm doing is flipping it over because we always keep the anode on the left-hand side and the cathode on the right-hand side. Do you see that? And so this is what I'm doing, all right? And I flipped it over so that I keep the anode on the same side because, you know, that's where the oxidation always takes place, but in reality we've actually reversed it, all right? And we no longer have to keep these two chambers separate from each other because we're not taking advantage of a spontaneous reaction, we're actually controlling the direction of the electron flow. And if we're controlling the direction of the electron flow, we don't have to keep the two chambers separate. We do not need a salt bridge anymore, all right? And therefore, what you end up with is this drawn here, okay? So you can see that this side will be the copper. So the anode will now be the copper electrode, and the cathode will be the zinc electrode, all right? And the anode has the oxidation, so copper solid will go to copper 2 plus 2 electrons here where the oxidation takes place. On the reduction side, we're going to have now the 2 electrons being picked up because that's where the reduction takes place. So you'll have zinc 2 plus picking up 2 electrons to give you zinc solid. Do you see that? So essentially what we've done is we've just drawn it, but we've reversed the 2 electrodes. What was anode used to be the zinc, now the anode is the copper, and the cathode used to be copper, but now the cathode is zinc. Got it? So now if I wanted to calculate the potential for this reaction, can everybody see the sign is going to be flipped? All right? So what we have is at the anode, I'll have copper solid going to copper 2 plus 2 electrons. Remember, this is the oxidation. And therefore, if I want to write the potential that corresponds to this, I would turn to the tables, pick the value that corresponds to that, but because it's an oxidation, I'm going to flip the sign, and the sign would be negative 0.34 volts. All right? In galvanic cell, this would be the reduction, and therefore the sign would be positive. All right? The value that you get from the tables will be plus 0.34 volts. But now, because this is the oxidation, I flip the sign around. Now, on this side, if I take the cathode, you can see that this is zinc 2 plus picking up 2 electrons to give you zinc solid. This is the reduction. This is the value that I would take from the tables. And in the tables, if you look at this value, this is negative 0.76 volts. All right? So for this reaction, you can see that copper solid plus zinc 2 plus gives me copper 2 plus zinc solid. And E naught cell for this would be negative, which is negative 1.10 volts. Do you see that? So for the electrolytic cell, your cell potential comes out to be a negative because this is a non-spontaneous process and we're driving it using an external voltage. Now can everybody see that? So if I want this reverse reaction to take place, I have to supply a minimum of 1.10 volts in that direction. Do you see that? So the minimum amount of external voltage that needs to be supplied to drive this reaction in this direction will be 1.10 volts. Can everybody see that? But it turns out in practice, you have to actually supply more. All right? So it's not like you have to supply exactly the amount that's required. You actually have to supply an extra amount to get the reaction to go. And the difference between this and the actual value that we supply is called an overpotential. So it's like you have to apply, depending on the substance that makes up that electrode. So if we're using copper and zinc, you know, each electrode has a value that's available in tables. And so it'll be like something like 0.6 volts. All right? So if you want to get this to go in this direction, not only do you need to supply an external source of 1.10 volts, but you may have to supply a little bit extra, which is approximately like 0.06 volts, which is called the overpotential. So you would supply this plus the overpotential, and so you have to supply something like 1.16 volts to get the reaction to go in that direction. Does that make sense to everybody? And you can read your textbook and they'll give you like, these are standard values. The overpotential are standard values that are listed in tables, and your textbook has like for platinum, if your electrode is a platinum, they give you what the value is, and you can look at the different materials and what the overpotential is for different materials. And essentially what it is that you have to supply more than what is required. This is the minimum amount that's required to get it to go in the reverse direction. Did you guys get it? All right, so let's take another example. Let's say that we have an electrolytic cell, and in this electrolytic cell, let's say the anode is where now the oxidation takes place, and you can have 2 Cl minus, giving you Cl2 gas plus 2 electrons. And if you look at the values for this in the table, it's about negative 136 volts. If you have at the cathode, you have magnesium, you have Mg2 plus aqueous picking up the 2 electrons to give you magnesium metal. And if you look at the tables for this value, it's at the cathode, it's where the reduction takes place, and this value comes directly from the tables. And therefore, if you want the whole cell potential for this, you add the 2 reactions up, so you have 2 Cl minus plus Mg2 plus, giving you Cl2 gas plus magnesium solid, and this will come out to be negative 3.72 volts. Okay? So the same underlying principles that we've learned for galvanic cells applies here, but you can see that in each instance here now, your cell potential, your overall cell potential will have a negative value because it is non-spontaneous, and so you can now know the minimum amount of voltage that needs to be supplied to drive the reaction in the opposite direction. Okay? Now, the electrolysis, the underlying principle in electrolysis or in electrolytic cells is what is used in the industry called electroplating. All of you have heard about, you know, you can buy jewelry that's electroplated. So electroplated means that, you know, you can make a necklace out of something like iron, which is relatively inexpensive, and then you take 18 karat gold, for example, and you electroplate the surface with it. All right? And this is how electroplating is done. Because what you do is, can you see that in this process, let's take this one. what happens is magnesium is being deposited at the cathode. So essentially what it is if you want an electroplate, you want a magnesium spoon, for example. You take a steel spoon or an iron spoon, and that would be your cathode. So the shape of the spoon is the cathode, and that's dipped in the solution. And now you supply the appropriate current, the voltage, all right, with the overpotential, and you drive the reaction. And essentially what happens, at one end you can see that chlorine gas is being produced. So chlorine gas will just come out, will bubble out. At the other end, your spoon, you're going to deposit magnesium on it, all right? And essentially what you will form is a thin layer of magnesium on the spoon, and then you'd stop it and you take the spoon out. If you wanted a gold-plated spoon, essentially what it is your spoon is your cathode, but now in your solution, you would set it up so that you have dissolved gold ions in solution, and those gold ions will deposit on the spoon so that now you have an electroplated spoon. If you've seen these silver-plated platters, that's exactly what it is. Your cathode is the platter. You make the platter out of an inexpensive material like iron or aluminum or whatever, and then on top of that, you're going to now electroplate it with silver or gold or whatever material it is, and that's what electroplating is. It's really taking advantage of an electrolytic cell, and we call that electrolysis. Okay? Now the last little bit that we're going to look at is that you should be able to calculate. So I've shown you how to calculate the minimum voltage that you need to drive the reaction in the opposite direction. So if you want this process to take place, you know that you have to supply the minimum amount of the voltage. And on top of that, you have to have the overpotential. Okay? And we looked at the fact that in an electrolytic cell, you don't need the salt bridge. All right? Everything can be in one setup because we have full control of the direction of the flow of the electrons. All right? And the circuit is completed by, you can have cations moving in this direction. You have anions moving in this direction. And so because you have cations and anions in that solution, as they move towards each electrode, and as they react at those electrodes, now you have a circuit completed within that setup. Okay? Now the last thing that we're going to do is actually a type of calculation that we carry out. And this is given by this handout that I placed on the class website. So now, if we want to calculate the amount of substance that are deposited during electrolysis. So we want to look at calculating the amount of products of electrolysis. So remember I said that the cathode is where we usually deposit solid material. So you can electroplate using you can electroplate any metal, all right? At any metal that you desire. It could be gold, silver, it could be aluminum, all right? Whatever material you want. And so a convenient calculation that we carry out is we want to know how much of the material actually deposited on the surface, all right? And when you do this, the calculations are in this way. So the calculations are based on Faraday's law of electrolysis. And what it says is, according to this law, is that the number of moles of product formed by an electric current is stoichiometrically equivalent to the number of moles of electrons supplied. So if you know the current that you're supplying, then from the current that you're supplying, you can figure out the number of moles of electrons that you supplied. If you know the number of moles of electrons you've supplied, remember the half reaction tells us, from the half reaction we know for every mole of electron that's taken up, we know how many moles of solid would be deposited. Do you see that? So that's kind of simply put, that's what we're doing. So we're going to start with the current that we supplied, and from the current we're going to try to figure out how many moles of electrons have we supplied to that electrolytic cell. And so you start with the amount of electricity, and electricity is always given in units of ampere. All right, so the current is given in terms of ampere, and how long, the time. All right, and so that gives you, and the time that we're using is per second. All right, so if you want to know the amount of charge that you supplied, The charge is always the current in amperes times the time in seconds. So if you take the current that you supplied and multiplied it by the time in seconds, what you end up with is the charge supplied, and that is in units of coulombs. So ampere times second. Ampere second is actually coulombs. Got it? So now you've taken the ampere, multiplied by the time. Now you know what the charge you've supplied is, which is coulombs. Now Faraday's constant gives us the charge per 1 mole. All right? So can everybody see that if I know the total charge and I know charge per mole, if I divide the total charge by charge per mole, I end up with the number of moles. It's like dividing mass by molar mass. Molar mass is grams per mole. Here, instead of mass and molar mass, we have charge and charge per mole. So if you take the charge and divide by charge per mole, which is Faraday's constant, what you end up with is number of moles of electrons that have been supplied. So now what we can do is, so you can see the moles of electrons is always the charge supplied, which is in coulombs, divided by the Faraday constant, which is F. All right? And that will give you the moles of electrons. So essentially what you do is you start with the amount of electricity and the time. You convert that to the charge in coulombs. You divide by Faraday's constant. You end up with the moles of electrons. Once you know the moles of electrons, you look at the balanced equation. So stoichiometry of the balanced equation. And from that, you can calculate moles of electrons to moles of products. All right? Once you know the moles of products, how do you convert moles of products to grams? You multiply by the molar mass. Got it? So now I want to take one example of a problem where you apply this. So this is like stoichiometric problems. And so if you turn to this, so once again, what I want you to be careful is don't get distracted by sort of distractors, okay? So this problem, when you read it, looks much harder than it really is. All right? And that's because there are some distractors there that can distract you from the real goal. What you have to tell yourself is, I need to go back to fundamental principles and just solve it from what I know. Okay? So let's take a look at this. Aluminum is produced by electrolysis. So we are producing aluminum by the electrolysis of aluminum oxide dissolved in molten cryolite. So cryolite is the solvent. So you're dissolving aluminum oxide in that substance. Calculate the mass of aluminum that can be produced in 1 day in an electrolytic cell operating continuously at 1 times 10 to the 5 amperes. Okay? So essentially what you're looking at is, don't get distracted. What you're looking at is, you're looking at aluminum starting off as this, all right, is depositing as aluminum solid. All right? So you have aluminum oxide dissolved in there, and this aluminum oxide is being deposited as aluminum. So I need to know N. I need to know how many electrons are being supplied. All right? And so can everybody see that if you look at this, if I assign oxidation numbers, can everybody see that this is 3 times -2? Therefore, each of these aluminums will be +3. Can you see that? There's 6 plus on this side, 6 minus on this side. If you look at this, what is the oxidation number of aluminum? So can everybody see that when aluminum goes to aluminum solid, how many electrons are involved? Each aluminum atom, each aluminum ion goes from +3 to 0. All right? Is that a reduction or an oxidation? Reduction. And you know that 3 electrons are being picked up. So for each, we're looking at 1 aluminum ion. Each aluminum ion will pick up 3 electrons. So that means for every mole of aluminum that's deposited, it needs 3 moles of electrons. Can everybody see that? So essentially what's happening is that aluminum 3 plus is picking up 3 electrons to give me aluminum solid. Okay? So now we can just do this problem in one single step. All right? So if I want to know grams of aluminum deposited, I start with the ampere, current. So I know current is in amperes times the time, which was 24 hours. I have to give this in seconds, so I'm going to convert 24 hours to seconds, and all of this will come out to be that. So 24 hours per minute, 60 minutes per hour, and then there are 60 seconds per minute. So that will be the time. So this is, if I multiply this by this, it's coulombs. I'm going to divide by Faraday's constant, which is 9.65 times 10 to the 4 coulombs per mole. So what I have got, this gives me the number of moles of electrons. All right? Now I know that this is number of moles per electron. In this equation, can everybody see that for every 1 mole of aluminum, how many moles of electrons do you need? 3, okay? So that means I can say for every 1 mole of aluminum, I need 3 moles of electrons. All right? So what I've got is moles of aluminum now. So can everybody see that the first step was calculating the number of moles of electrons. The number of moles of electrons, I know that for every 3 moles of electrons, there's 1 mole of aluminum. Now I'm going to multiply by the molar mass of aluminum, which is 26.98 grams per mole. And so what I end up with is 8.05 times 10 to the 5 grams of aluminum. Okay? Just to keep track of significant figures, and since I'm using everything to 3 sig figs, can you change this to 3 significant figures so that your answer comes out to 3 significant figures? So if your ampere is 2 sig figs, this will come out to 2 sig figs. If you make it to 3 sig figs, that gives you the grams of aluminum that will be deposited. All right? Yes?
Is it going to be on the midterm, all this material?